much, Leia, for that nice introduction, and thank you to everyone for coming. I'm really excited to tell you a bit about moduli spaces of curves. I really love getting questions during a talk, so if you have any questions at any point, please just ask. And I actually have a question for you guys to get started. So I put this question in the abstract too, and it asks, given 3 circles, how many other circles are tangent to all 3? So did anybody think about this question? Does anyone want to share an answer? Yeah, in front?
I mean, I didn't do it myself, but there are 8.
Yes, okay, did anyone else get 8? Okay, so 8 is the answer here. I'll draw a few of them. So here's 1, 2, 3, 4, 5, 6, 7. Does anyone want to see what the last one is? All the way around. All right, so today I want to tell you what algebraic geometry has to say about questions like this and how some of the tools that help us answer this question are related to my research. So algebraic geometry is what it sounds like. It's about a relationship between algebra or polynomial equations and geometry, which is the study of shapes. So an example of a polynomial equation would be x squared plus y squared equals 1. And if I plot all the solutions to that equation in the plane, you'll see we get a shape. In this case, it is the unit circle. Now, in algebraic geometry, we often don't just care about the individual shapes that we get in this way, but we care about understanding all the shapes of a given kind and how they relate to each other. So something that helps us do that is called a moduli space. So a moduli space is a space where each point in it corresponds to an object of some fixed type. So, for example, a circle is determined by its center let's say it's at AB, and its radius, let's call it R, which is some positive number. And so, the moduli space of circles is a 3-dimensional space. It's the set of all triples, A, B, and R, where R is positive. There's this positive R direction inside of a copy of R3 with coordinates A, B, and R. So for example, this unit circle from the beginning is going to correspond to the point right here. You 0, 0, 1. So now let's suppose we fix one circle. And we ask to describe all of the circles tangent to that one fixed circle. So there's a couple cases for what this might look like. But let's consider, as a first case, when our fixed circle is in black here, and we're looking for circles tangent to it, not contained or containing it. So one that sort of meets it on the outside like this. So let's say that our fixed circle here has center A naught, B naught, and radius R naught. And we're looking for blue circles tangent to it. Those are going to have some radius R and center AB. So what can I figure out about the blue AB and R? Well, let's drop a perpendicular here. So I make this right triangle. Then, this horizontal distance is A minus A naught. And this vertical distance is B minus B naught. And the hypotenuse here is R plus R naught. So, by the Pythagorean theorem, I learned that I must have A minus A naught squared plus B minus B naught squared is R plus R naught squared. Any questions about that so far? So something pretty cool has actually already happened, which is the circles with this property of being tangent to our fixed circle are again described by a polynomial equation, this time on the moduli space. So that equation that we just found, you might recognize as the equation of a cone with center A naught, B naught minus R naught. So if our fixed circle was like up here at A naught, B naught, R naught in the moduli space, you should picture its reflection being the cone point of a cone. So these circles that I'm drawing in blue are on some surface that looks like this. So one way you can think about this also, if you set the blue R here to be 0, then it's saying that A and B are constrained to satisfy the equation of our original circle. So this here in the R0 plane is our original circle. And that kind of makes sense. Think about like if this blue circle had radius 0, it would kind of shrink down until it were right on the edge of that fixed black circle. Okay, any questions about case 1? Okay, so now let's go on to case, yeah? All right, case 2 is when one of the circles contains the other. going to look something like this. Here we have our fixed circle in black, and we're looking for circles like this blue one, tangent but inside. So now we can do a sort of similar thing. This circle here, right, has radius r and center AB. And the black circle has radius r naught. So this distance here between their centers, as I've drawn it, is r naught minus r. And now I'm going to draw perpendiculars again, form this right triangle. And the side lengths are again a minus a naught and b minus b naught. So now I learn that a minus a naught squared plus b minus b naught squared is equal to r naught minus r all squared. And now this, again, right, we've got a polynomial equation on the moduli space. This time it's the equation of a cone whose center is at a naught, b naught, r naught. So these blue circles here are going to lie on this cone with vertex right here. And what I've drawn here is when r is smaller than r naught, then it'll look like it's inside. But actually the same equations describe this situation when r is bigger than r naught. Those will sort of be the top part of the cone given by that same equation. Any questions at all about this? Yes, please.
Is the additional cone we get up top from just like exchanging r naught with r because the square doesn't really change much?
Right, exactly. So if I were to carry out the same analysis again with the bigger blue circle and pretending it was, I had the bigger blue circle and the smaller black circle, then I would write down the very same equations, but I would just be flipping blue and black. And then you notice in this equation, if you flip blue and black, you get the same equation.
Okay.
Yeah, great question. Thank you.
Of course.
More questions?
Does the shape on the graph, or if you pick something other than a circle-sided square, would you get a cube, or?
Well, if you pick something different from a circle.
So, yeah, instead of, because a circle into a cone has.
Right, you would get a more complicated shape, but it would again be true, and this is sort of one of the wonderful things about algebraic geometry, that if we were looking for curves of a fixed type tangent to that fixed curve that was defined by polynomial equation, the subset of the moduli space would also be defined by some polynomial equations. All right. So I want to share now an animation with you that one of my friends made for me. And it's an animation of the moduli space of circles, as we were just discussing. Oh, unblink. Great. So on the left is the moduli space. You can see there's a moving point, and on the right we are always picturing the circle that corresponds to that point. So right now we're moving around in fixed height in the moduli space, and so that circle was just saying same radius. But now, if I start moving up and down in the moduli space, then the radius of that circle will get bigger or smaller. So in a moment, we're going to now fix a particular circle, and these moving circles that are coming in are different circles that are tangent to this fixed circle. And so let's see what happens. So you might notice that they're starting to trace out this surface whose equations we just derived using the Pythagorean theorem. So altogether, all the circles tangent to that fixed circle are this blue surface. But now we had this question of how many circles are tangent to 3 fixed circles. So what if I had a second fixed circle? Then there would be those 2 surfaces in blue, and they would intersect along a curve that's now being traced out in green. So the whole curve's worth of circles tangent to 2 fixed circles. And then when I add in a third fixed circle, there's finitely many points of the intersection of that curve with that last surface, and those are the 8 circles that are tangent to our 3 fixed circles. All right, so that is an example of what I mean by doing intersection theory on a moduli space. So we were trying to understand how 3 different shapes of this kind intersected with each other. And my research is about intersection theory on some other moduli spaces of curves. But before I go on to these other moduli spaces of curves, I want to see if there are any more questions about the circles problem. Yes?
If 2 circles were already tangent to each other at the beginning, would you get fewer solutions then?
Yes, so it is possible that you will get fewer solutions. And in fact, I was sort of hoping somebody might ask me, are there always 8 solutions here? And the answer is no. And part of the reason has to do with the fact that if you take a polynomial with real coefficients, its solutions are not always real numbers, right? So we see this already if I take, for example, just the polynomial y equals x squared, right? If I intersect that with the line y equals 1, right, there's 2 points of intersection. But when I intersect with the line y equals minus 1, I see no points of intersection. But if I decided to work over the complex numbers instead, there would be some intersection points here. So over the complex numbers, the line y equals minus 1 meets the curve y equals x squared at the 2 points plus or minus I, comma, minus 1. So something sort of similar can happen in this circles question, right? We're intersecting a bunch of quadratic equations on this moduli space, and it could turn out that the solutions have complex values for A, B, and R. And so you won't see those solutions. But if you sort of enlarge your world to contain some appropriate notion of a complex circle, then there will always be 8. With an additional caveat called counted with multiplicity, which has to do with, well, okay, this line, y equals minus 1, right, is meeting our curve in 2 points. When I go down to the line of y equals 0, right, it's as if those 2 points have collided. And I sort of want to count that with multiplicity too. Yeah. So for this reason, this sort of funny thing where the answer can change over the real numbers, but not over the complex numbers, algebraic geometry is often easier when we work with the complex numbers. So the complex numbers are going to come up in this second part of the talk, when I tell you about these other moduli spaces of curves that I studied. Oh, yes, please.
This is somewhat of a follow-up question. I was
Yeah.
wondering this moments ago. Are any other fields studied? Are any other underlying fields allowed? Say, p-adics or z mod pz?
Oh, well, so there's actually been a very recent development in enumerative algebraic geometry. It was in 2017 by Cass and Wickelgren. Came up with a means of giving counts of problems like this over other fields, including, finite fields. And it's difficult to picture at that point, but yeah, the theory has been extended in that direction. Yeah. More questions? All right, so these moduli spaces of curves that I study are what I call abstract curves. So to introduce that idea, I want to explain to you why, in fact, all circles are the same abstract curve. Right? They can sit in the plane in different ways, but I'm going to give you a sort of abstract description. So I'm going to show you that they are all a copy of the real numbers union a point at infinity. And the way we're going to see this is by something called stereographic projection. So suppose you have some circle, any circle, and you're going to take a point on that circle. Maybe you could say it was the unit circle, maybe that point is 0, 1, and start projecting from that point. So we're going to declare that each point on the circle is mapped to the real line by whatever point that red line meets this horizontal black line at. And this works just as well for a point down here. Point down here would wind up being sent to that point there. So this is a one-to-one map from every point on the circle besides this top point to a point on the real line. So what happens as I start approaching this point at the top? Well, these lines start to become closer and closer to horizontal. And this intersection point starts running off to infinity. And so we say that this point at the top is sent to infinity. It corresponds to that dashed red line eventually becoming parallel to to the horizontal black one. So you can actually write out the rules for this map. You can calculate what this t is in terms of x and y. And you can also write down the inverse map, which I'll show you, is t goes to 2t over t squared plus 1, comma, t squared minus 1 over t squared plus 1. And this is called the rational parameterization of the circle. So it turns out, not only does this tell us about all of the real solutions to x squared plus y squared equals 1, it also parameterizes all of the complex solutions. So the set of pairs x, y in C2, so that x squared plus y squared is 1. Was that a question? What's C2?
Yeah.
So I just mean x and y are both complex numbers. Yeah, so I'm looking at pairs of complex numbers that satisfy this equation. And I claim that set is, in fact, a copy of the complex numbers minus 2 points, plus or minus I, union a point at infinity. So this deserves a little explanation. What I'm saying is that there's a map from complex numbers to pairs of complex numbers, where I send t to this pair. But of course, this is not defined if t squared plus 1 is 0. So I had to leave out plus and minus I. And then as I sort of said here before, the point t equals infinity actually should correspond to a solution. You see that if I take the limit as t goes to infinity of both of these expressions, you'll see that you do get back 0, 1. Now, much in the same way that the real numbers union that point at infinity could wrap up into the circle, the complex numbers union a point at infinity wrap up into a sphere. So I could also think about this as being the sphere, so that's C union a point at infinity, but with 2 points missing. So this is what I would call sort of the complex version of the abstract version of my curve. And this is called a Riemann surface. And it has an invariant, which is called its genus. And the genus is the number of holes of the whole shape. And a sphere has genus 0. Any questions about this? I know we're ramping up here.
Does removing isolated points not affect the genus?
So when I'll say that the Riemann surface I want to be the sphere, and then I'll say the surface has genus 0, and then let's say with 2 points removed. Yes, please.
Is that sort of saying, like, if we had a chorus or something, then it would be like genus 1? Or
Yes. In fact, I wanted to talk about the genus 1 case next. Yeah. Great. So yeah, let's go on to genus 1. So this genus 0 case came up when I started with this degree 2 equation in the plane. And it turns out that any degree 2 equation has an associated complex abstract curve, which is genus 0. And they're, in some sense, they're all the same one. There's like only one genus 0 Riemann surface. But the same is not true in genus 1. And this comes up already when we use degree 3 equations. So I'm going to take, again, pairs of complex numbers that satisfy some degree 3 equation like this. And it turns out that these can, again, the set of all solutions to this cubic equation can be parameterized by the complex numbers, but not in a one-to-one way. So there exists a map from the complex numbers to this set of solutions. Technically speaking, should be this set of solutions union an infinite solution. So if I draw the real solutions to this equation, it looks something like this. And you see this curve it kind of runs off to infinity. We want to pretend there's another point off there. All right, so but I'm not just trying to parameterize the real solutions, I'm trying to tell you about all of the complex solutions to this equation. And I claim they're going to come to us from a map from C to this set, but it has the property that there will be a subgroup inside C. I'll call it lambda. So that entire subgroup, lambda, is sent to this infinite point. And so this, I can say more precisely, this is a subgroup Z2, by which I mean a collection of points that look like all integer multiples of 1 and some fixed complex number. Or you can just picture this collection of red dots. And so the way this map works is it wraps up C onto itself in such a way that if 2 points have a difference which lies in the red set, then they're sent to the same point. Another way to say that is I'm actually saying this map is a map. It's like the quotient map. You just view this as a subgroup of this. And every coset is represented by in this region here. And so what this map looks like is you could picture every point is equivalent to something in this region, and then the opposite edges here are also equivalent. And so this wraps up into a torus. And of course there's a point that was this infinite point on it. So this is a genus 1 Riemann surface. But it turns out that if I change these coefficients, A and B, then the shape of this collection of red dots also changes, right? Instead of looking like this, maybe they would look like the fundamental domain could look like this, right? Something of a different shape. And when you have a different shaped, oh, question, please.
Yeah, with the A and B, is it always going to skew the lattice points, or like expand? Does it rotate?
Good, all good questions. So what happens is that if two lattices are the same shape up to scaling, then it corresponds to sort of the same genus 1 Riemann surface. And if they are truly different, like they cannot be scaled into one another, then they correspond to different genus 1 Riemann surfaces. And the relationship between the lattice and the A and B is a little bit complicated, but roughly it's close to being that the A and B and the lattice are the same information, but not quite. Yeah?
Wait, so when you mentioned that the mapping from C to like that set is not one-to-one, do you mean that every parallelogram maps to a torus? Or-
Yes, it's like all of these, like there's all these parallelograms, and there's sort of, each one of them is being sent, kind of wrapping up, like this one and this one. It's like, you could picture, see, like, I'm going to draw this purple line segment here. It would be like that segment will wind up kind of looping around here twice. Can you picture that?
Yeah. And so, sorry, I didn't follow. What was the significance of these red points again? Like, where do they map on to the...
So yeah, all of the red points wind up getting sent to one point when we do this wrapping business. Yeah, more questions?
So what does the red point represent?
The red point represents either you could say a point at infinity, or you could say it represents a point where the map, or like the red dots, all of them over here, are points where the map from C to just the subset of finite solutions is not defined. In some ways, they're sort of analogous to these, like, plus and minus I, where this parameterization was not defined. More questions? Yes?
What are the, like, what's the relationship between the cosets, like, geometrically?
each correspond to a point on this genus 1 surface. Yeah. Yes, please.
Instead of working over c squared, do you sometimes work over like p squared? So like you add a couple of points to fill in those holes there?
Oh, yeah, projective space?
Yeah.
Yes, absolutely. And in fact, yeah, that is sort of what I've been, I wasn't going to precisely define projective space, but that would sort of fix these issues of this, where this map is not defined. It would precisely being sent to infinity in the projective space. Thank you. Okay, so I told you that sort of as if you have different shaped lattices, you can really get different genus 1 Riemann surfaces. And so there is a moduli space of genus 1 Riemann surfaces. It turns out it's a one-dimensional moduli space. And more generally, there are Riemann surfaces of every genus. So those will look something like this, where I've got G holes here. And we can study their moduli space. And it's called MG. So you should picture that is some big space where each point in this space corresponds to a different genus G Riemann surface. And people have been interested in the intersection theory of this moduli space. So let me tell you how people study the intersection theory of this space. So we study the intersection theory of MG with something called its Chow ring. So this is a graded ring where the elements in this ring correspond to the algebraically defined subsets up to some equivalence relation. Right? So remember, the intersection theory is about, you have some subsets here defined by polynomial equations, and this is a gadget whose elements keep track of those different types types of subsets we might be interested in intersecting. And then the addition operation in this ring corresponds to taking the union of subsets, and the multiplication operation corresponds to taking intersections. And finally, the grading is by the dimension, or co-dimension, of these subsets. Maybe I'll say a word about this. The co-dimension is something about how much smaller is that subset than the dimension of the whole space. And when you intersect things that are smaller than the whole space by a certain amount, you expect if you intersect one thing that's smaller by A and one thing that's smaller by B, you should get something that's even smaller by A plus B. So I'll tell you what was previously known about the intersection theory of MG. So when G is 2, this Chow ring was determined by Mumford. This was back in 1983. And then for genus 3 and 4, there are 2 papers of Faber from 1990 that determine that Chow ring. G equals 5 was determined by Izadi in 1995, and then G equals 6 by Penev and Vakil in 2015. So each of these papers brought a new perspective to thinking about this moduli space, MG, and its intersection theory. And in some ways, each one sort of was able to redo the ones previous. And the theorem of mind that I want to state is joint work with my collaborator, Samir Canning, and we determined the Chow ring of MG when G is 7, 8, or 9. So that is the result I'd like to end with, and I'd be very happy to take any questions. Yes, please.
Is the field the same one that was your PhD advisor?
Yes, in fact, Ravi Vakil is my PhD advisor, and Elham Izadi is Samir's PhD advisor. Yeah, please.
So you said that the moduli space for genus 1 surfaces is one-dimensional. What are the dimensions of the other ones? What about 2 or 3?
Mm-hmm. So in general, this thing, MG, has dimension 3G minus 3. So it gets bigger as the genus gets bigger. And 1 is actually a little bit funny. It has to do with the fact that elliptic curves, or genus 1 Riemann surfaces, have lots of symmetries. And when you have that many symmetries, kind of weird things can happen to the moduli space. But for all g greater than or equal to 2, this formula holds. Yes, please.
So I see that like most of these like elements are like individual, like 5 and 6 are independent of each other. Was there something special that allowed you to do 7, 8, and 9 all at once, or were they also like individual things that you found?
Well, so our approach sort of was introducing a certain new idea that kind of got all of 7, 8, and 9, and again, can treat all of the past, the smaller genera.
So is there something more complicated with 10, or?
Yes. Yeah. What seems to be complicated about 10 is that we don't know how to understand a general genus 10 curve. So maybe one way to explain what we did here in genus 7, 8, and 9 is that we used a related moduli space. So there's a moduli space called the Hertz space. And we studied this space for some, this is a space that has two parameters, k and g. We understood it when k was small. And these help us understand basically all of the curves in genus 7, 8, and 9. But then it sort of runs out in genus 10. There's still a map from this Hertz space to M10, but it kind of lands inside of some smaller dimensional subset. Yeah?
Is anyone working on genus 10 right now?
Well, I'm planning to. So we'll see how it goes. So, yeah. Yes, please.
Because we're working in algebraic geometry, do we have a very specific polynomial description of these genus G moduli spaces?
NG?
Yes.
So I would say there's
I'm sorry.
I would say no, unfortunately.
Okay, because the alternative I was going to give, because I'm rather interested in like differential geometry, is it more of a local description?
Yeah, so we have some understanding of the local geometry of this space, for sure. And we do know that it is possible to put this space, MG, inside of some large space.
Like Whitney.
Yeah, but furthermore, where it is the solutions to a collection of a bunch of polynomial equations. So meaning this is an algebraic variety.
Okay.
But I think nobody has any idea what those equations are. Yeah, these are great questions.
Any more questions for Hannah?
Yes, please.
Sorry, you said there are multiple curves of genus 1, right?
Yeah, you could sort of picture that the moduli space of genus 1 curves is one-dimensional.
Okay.
Yeah.
So there's only like
There's not.
one kind.
They vary in a one-parameter family, is what I would say. So there's something called the J invariant of an elliptic curve. It's a single complex number. And if you know that J invariant, then you know which elliptic curve it is, which genus 1 Riemann surface, up to isomorphism. Whereas, to sort of know where you are in this MG, you would need to be specifying locally 3G minus 3 different parameters. Yeah?
Can you give another example of Riemann surface of genus 1 that's not the torus that we're picturing?
No, so all of the smooth genus 1 Riemann, like all genus 1 Riemann surfaces are that torus.
Okay.
So it's kind of funny because the underlying topological space is all the same, right? They all are just this torus. But somehow the structure of the Riemann surface remembers how we wrote it as C modulo a lattice. And the different shapes of that lattice is what gives rise to that moduli. Yes?
And so the shape of this lattice can be determined by just one parameter? Or
Mm-hmm. Yeah, one complex parameter.
Any more questions?
Yes?
Sorry, so that's like a little bit akin to starting our circle like one-to-one function from a different point than the 0, 1 that we selected at the beginning, right? It's like setting a different point infinity or a different point infinity.
So again, this is connected. There's some of the weirdness of genus 1. As I said, there's a lot of symmetries. So marking there's like a distinguished point. And as you sort of, if you were to move that point, they're all isomorphic to each other. Because it turns out there's like this translational symmetry that can sort of send any point to any other point.
I just realized my question made no sense.
Oh, okay.
Let's save other questions for after the talk.